So what we are talking about today in our webinar is modeling complex cable harnesses in EMA3D simulations. First, let me start off by introducing our company. We are Electromagnetic Applications, or EMA for short. We have a handful of expert PhD level EM analysts in our company, and we have been doing this kind of work for 39 years. We are located in Lakewood, Colorado, which is a suburb of Denver. It's a beautiful area. We'd love for you all to come and see us sometime. And if you were looking for additional information about our company or what we do or trainings or information about our services, please visit our website at EMA3D.com. So a little bit more about EMA is that we do provide both software commercially available that you can purchase, but we also do consulting services. Our software is EMA3D, which is a full wave 3D solver, and we also have M-Harness, which is a transmission line solver for cable harnesses, and we have integrated the cable solver into our full wave solver. You can purchase or use either of these software separately or in an integrated form. These tools have a very long validation heritage on real aerospace platforms. We have been doing this type of analysis with our software since the 80s, and we have validated it on a multitude of aerospace platforms and environments, and we still do it to this day. You will find that the capability of these tools compared to others are quite good, and what we offer is in the lowest rate of cost for this type of tool that you'll find in the market. And as well as the software tools and consulting services, we also provide expert level support for our software. And usually we'll get back to you on the same day or help you solve your problem when you are using the tools. And because we own these tools and we provide consulting services, we can do custom integrations to help you solve whatever electromagnetic problem you're having. As Nils mentioned at the introduction, this webinar series is provided for free by EMA, and it's an educational series that we're trying to tackle or review topics that are pertinent or interesting to the industry. And as I mentioned before, please visit our website, EMA3D.com, or feel free to contact us by email. My email is Cody, C-O-D-Y, at EMA3D.com. Also tuned in is Jennifer and Tim. We are all available to answer any questions you might have. So let's dig into the webinar. What we are talking about today is cable harnesses, and I'm going to review some cable coupling and transient analysis techniques, how we use simulations to solve these problems, what are some typical certification steps when dealing with cable harnesses, and how we handle these complex harnesses in our modeling approach. How, once you have imported cables, how do we simplify and assign the appropriate cable harness details to our models. And then lastly, we will talk about the importance of validation and how you might validate your analysis approach. So as we all know, cable harnesses exist in every aerospace vehicle or system. They can be quite complex and often occur late in the design and are implemented as one of the last aspects of a particular vehicle. These vehicles are exposed to a multitude of environments, including lightning. When you're dealing with cables, it would be on the indirect effects form of lightning. And HERF environments, you have low-level coupling to these cables. And then you also have EMP or EMI, EMC environments that you have to understand and evaluate your system for. When you're looking at cables, you want to understand the actual transient levels. So this is what currents and voltages will couple to your cables and electronic systems. These need to be analyzed so that you can verify your system, vehicle, or box functionality and safety in the presence of the different environments. So when you're considering how to determine cable transients, there's several approaches you can take. The approach that you take will depend on the amount of time that you have, the accuracy that you need for your results, and the available information that you have on your system. So initially, you can do simple formulas or engineering estimates. This is where you take an equation, plug some parameters in, and get a ballpark value. And so this provides a basic understanding of your problem or initial levels that you might see for your coupling transients. A step up from this is a canonical or submodel. When I say canonical, I mean a simple representation of your vehicle or system that you're trying to model. And these are very good for performing parameter studies. If you change, say, a conductivity of a skin, you can evaluate how that might affect cable transient coupling beneath that skin. And it's also good for evaluating design features in a particular problem. If you're just looking at an area of your wing or an area of your radome and you want to see how adding bond straps or lightning strips might impact the coupling beneath that area, you can use a submodel for that. But lastly, the focus of this presentation and what we're going to talk about is a high-fidelity model. This is where you include many details of your vehicle or platform that you're trying to analyze into a simulation model. This allows you to do a full vehicle coupling analysis where you can look at many different areas in a single simulation, many different regions of your aircraft. It provides very high accuracy results that can be ultimately used for certification support or a very detailed understanding of the type of coupling you might see to your vehicle. So I'll talk quickly about canonical modeling and its benefits. I'll mention that as a very frequent user of the simulation software, I often build canonical models to sort of develop an initial understanding of a coupling problem. They are extremely valuable in your overall analysis process. They have a very quick setup time. They simulate very quickly. As I mentioned before, they are amenable to parameter studies, and they provide a very reasonable understanding of a particular phenomena that you're trying to study. So here's an example of a canonical wing that I put together to look at cable transients in the leading and trailing edges. Here's another example of a canonical model that was put together to analyze cable coupling in a HERF environment. It's a very simple fuselage model, and the goal of this was to change the complexity of cable harnesses to understand how adding complexities to those models changes the coupling response on a basic level. And what we found is that by doing a single wire or sort of a bulk representation of a harness is just not adequate to produce accurate coupling results. So what we did was start with a single wire harness and couple a HERF environment to it and look at the response. And as you increase the complexity of that harness by adding branches, adding multiple conductors, you see that it completely changes the resonance of that cable, as you might imagine, and also lowers the amplitude of coupling because of the dissipation associated with the complexities. So we went through a sequence of model features by changing the variation of packing within the cable, by looking at branching, sort of a standard branching, which is like a big branch, and then a micro branch, which might be a breakout at a box location. And we started combining these features. And what we found is that you can reduce the coupling levels in this canonical model by almost a factor of 100, about 40 dB as you add complexities. So this gave us some intuition that if you want to model cables in complex systems, that you need to include those complexities in order to get the right answers. So now I'll switch over to the high-fidelity simulations. That's the main focus of this presentation and webinar. So we use high-fidelity modeling simulations to help evaluate and improve designs of particular systems. You can look at how adding bond straps or adjusting connectivity across joints will impact your transient coupling. You can, as I mentioned before, look at a complete system response of a particular vehicle. So by having the details of the model in place and looking at different environments, you can analyze how coupling might be most severe in certain regions of your aircraft or what areas are most prone to high transient coupling. And then also you can use these high-fidelity models to complement a test program, or the ultimate goal is to reduce the amount of tests that you have to perform for certification purposes. So in the policy guidance material, there are typical certification steps that a aircraft manufacturer must go through when achieving or applying or obtaining their certification for their vehicle. So what we're focusing on is electronics, cables, and systems. So in ARP 5415, which is the user's manual for certification of aircraft electrical electronic systems or indirect effects of lightning, it states that you can use simulation analysis to certify an aircraft for indirect effects of lightning. And what it outlines in that document is an analysis plan which has elements that you should include in your process for certification. And this includes outlining the analysis technique proposed. And what we're covering today is such an analysis technique that you can use for this certification step. By creating these high-fidelity simulation models, you can analyze your entire system, and that's what we're proposing. Very important aspects of your plan should include key analytical model input data. This is how you're obtaining parameters in your model. Where do you get the geometry from? Is it created by hand or is it imported from CAD? What parameters are you including for your conductivities, your resistances, your transfer impedances? Where does that data come from? And it's all very important for your model development and certification process. Also, you have to set and show that your analysis techniques and results are valid for the particular vehicle you're trying to solve. So you have to go through a validation effort to do so. And you must understand the sensitivity of your model and technique to variations of parameters, which is very good for simulations, that you can tweak parameters in your model and re-simulate in a very efficient manner to understand the sensitivity of your model to those variations. And ultimately, you must define then, based on your validation and sensitivity exploration, margins that are associated with your numerical analysis. And one other thing I'll point out is that in the Advisory Circular 20-136B for protection of aircraft electronic systems against indirect effects, it specifically states that you may use aircraft analysis to determine ATLs and to see ARP 5415 for guidance. But the acceptance of the analysis method you choose depends on the accuracy of your method. So it's critical that you go through that validation effort. And anytime you're doing analysis or a program for certification, you must review this with your cognizant ACO to make sure that you're all on the same page for your certification. So for our high-fidelity models, we have used in the past and recommend many companies use this type of analysis for their certification program. One of the hurdles in the past has been being able to implement complex cable systems in a full vehicle. It has taken a long time, but we have found these results to be very accurate and very valuable for the integrators. And with our tools that we have available, EMA3D with integrated M-harness, you can model your entire vehicle down to individual pin transients in single simulation. So here's some of the typical steps that we use for our high-fidelity models. We will measure or determine the structural material properties or cable transfer impedances. These are the key inputs from the analysis plan discussed before. And then we will also do the importation and preparation of geometry for our CEM simulation. Now, these determining of key model inputs can be done in parallel with the preparation of model for simulation. And after you have your basic structural representation of your vehicle, you have to define your cable harnesses in detailed form from interconnect drawings and cabling schematics. And once you've incorporated all that information into your model, then you simulate and determine transients on cables, and then you can determine for test purposes which DO160 waveform and levels are appropriate for your particular electronics boxes. So a way you might determine some key model inputs, which are very important for your accuracy of your model, are through some kind of measurement program. This is something that EMA can also perform. We have done in many programs to analyze the types of materials that are being implemented into the particular vehicle we're analyzing, and we can measure and quantify the conductivities associated with complex composite stacks in the presence of ECF or without, and also characterize fastener impedance associated with critical joints in those particular designs. So these are some things that you need to know with very good accuracy as model inputs for your high-fidelity models. Typically, we start out with a CAD import process where you use your manufacturing CAD data that's supplied by your structural engineers and other engineers, and we import that into our CAD preprocessor. And then we will prepare all of the structures and interfaces in that model for CEM simulation. And this includes both the exterior components, the outer mold line, as well as the interior components that are critical, which includes cables, your avionics boxes, your engines, your bulkheads, things that would impact your coupling transients. So what we have done in recent years is sort of simplify the modeling of cables. We have some automated approaches now to simplify cables from an imported CAD. And we have a wizard that's available, and I'll show a demonstration today of how you can rapidly specify cable harness details based on your wiring information. And then we can also co-simulate your harness model, your transmission line model, with the 3D simulations to resolve all the details of your branches, shields, and conductors. So here we have a video showing how we would take an imported CAD information for cable harnesses and simplify it for our simulation. Let's see here. If I can get it to play. Just give me one moment. There we go. Apparently you can't have the laser pointer on and click play at the same time. So what I'm doing now is just showing the imported geometry of the aircraft that we will be looking at for this analysis. As you look inside, you can see the imported electronics boxes and cables. Obviously, this is a simplified version and is not meant to be exactly duplicating any particular aircraft or design. This is for educational purposes only. As we look in, we can see that there are connections of cables to electronics boxes in the mid portion of the aircraft and also in the avionics or forward portion of the aircraft. If we were going to go through and reduce these imported cables to lines that we would typically use for our harness definition, it would take quite a long time. And as you can see, as I select now, you can see that multiple bodies are often used to represent cable harnesses that are imported as they define the sections, and these bodies can link up with other sections to form branches in a cable harness. In order to input the necessary information into our finite difference model, we have to sort of reduce these bodies to a single line that we can apply our transmission line characteristics to. And so what we do is we use a tool that we have. It's our Cable Simplify tool. And what you can do is enter a set name or identify the cables that you're going to use for this analysis and basically hit go. And it's going to create simplified representations of all these imported cables. I'm just going to look at the left side here rather than look at the entire aircraft for simplification purposes. So after you put in the necessary information and hit go, it's now computing the center lines for all of those bodies that you have for your original imported cables. For the amount of information that we have here, it would take about 10 minutes to go through and produce all of these simplified lines, which is relatively quick in an automation process. But I've skipped ahead here to the point where all simplifications are finished. And now let's look at these simplified representations that we have. So as I add the simplified cables to the plot, you can see that they very nicely overlay the original routing of cables. This is important to maintain this routing because as you move your cables away from your structures in your vehicle, it can affect the coupling. And if you have intersections of your cables with your structures, it can produce unwanted results. So this is a nice way to simplify the original CAD without oversimplifying it. And this is very good for our definition process. So this video is done, and we'll move along now. So now that you have your routing or geometrical representation of your cables in your model, you have to assign the appropriate details of that cable to your wires. And these types of things that you need are the type of wire that you're looking at. Is it a shielded twisted pair? Is it a coax? Is it an unshielded wire? You need to understand the gauge of the wire, determination impedances associated with your cables. If there are any circuit loads that you want to include in your analysis, oftentimes for ATL analysis, you're looking at the most severe case, which is commonly referred to as the open circuit voltage or the short circuit current. So in these cases, we will ignore the actual circuit loads in the electronics box, and we'll either short the cable on both ends or short it on one end and leave it open on the other to determine the short circuit current and open circuit voltage. And something else that you would need to know are some shield properties, the transfer impedance associated with the shields that you're using. Now this is it can be a lot of information to gather when putting together a model. And we have tried to do our best to help out in the sense that we have a database of information for resistances, diameters, transfer impedances that we have measured or determined on our own for typical type of aerospace cables. You'll still have to go through the process of determining which cables are in your design, but we have in our tools a stored database of information for different types of cables that we have, in the most cases, measured ourselves. So now we'll go through a demonstration of how you might implement those features to your cables. So the tool that we have for this is called the M-Harness Wizard. And so it's a tutorial GUI that walks the user through the necessary inputs in order to create a workable transmission line model. And again, this transmission line model can be run integrated with your full 3D model or separately with the M-Harness solver. So anytime we put together a model, I'll just show you real quick, this is what we call a configuration control document. This is where we keep track of all the different components in our model, and we take snapshots of it, and then we keep track of the type of material associated with it, the conductivity of that material, thickness of it, and what assumptions we use in our model, what kind of conductivity we use to represent that component in our model. This is a very quick way for a non-CAD user to see what's in the model. So we also do this for our cables. So this is a simplified representation here of what our cable information might be like in our vehicle. I've broken it down into several different cables, showing the name of it, the gauge of the wire, the type of the cable that will be used, and then as well as the number of cables of that type in a particular bundle. So for this demonstration, I'm just going to focus on one of the cables. And I'm going to input this information that we have here based on routing, connection, wire type into our cable model. So for that, we will open up our M-Harness Wizard, which is in our M-Harness cable section, number 9 of our toolbox. And here is the tutorial. So basically, it says that we have stored data in our tool for resistances, diameters, transfer impedances, and you are welcome to use that, and we feel it's a good representation of actual cables. But if you have measured data or a different type of cable, you should put that in for your parameters. So it initially guides you through some basic steps. What cable are you working with? What level of shielding do you have for your cable? Do you have an overbraid with cable shields and interconductors, or do you just have like TSPs, where you have cable shields and conductors, or are there no shields at all? So this is something you need to be aware of going into your definition. And then because we have one level of shielding, there are a couple of ways to model this in our software. You can model it as overbrays and cable shields, where you're neglecting the interconductors, or you can model it as cable shields and core wires, which is more typical. And so we're going to be looking at cable shields and core wires for this definition. Now what it's asking you to do is go through and identify the sequence of routing that you might use for your particular cable. You can just input the set that has all of your lines and click return on it to add that information, or you can select the individual lines that you want to use for your initial cable definition. Now I'm just focusing on one cable for this definition for the sake of demonstration, but you can define as many cable harness definitions as you want with this tool. And you can do it in a single shot, or you can do it with a multiple runs through this wizard. So when we ask for a naming convention, you can input your complex cable names that are often associated with your harnesses. I don't know where they come up with these names, but they are often very lengthy and awkward to deal with. For our analysis purposes, it doesn't really matter what that name is so long as we have the right information for that harness. So I prefer to call them by simple segment names, broken down in a sequential fashion that just makes more sense to me. And you have the option to automatically name these, or you can input every harness name that you want for your definition. Now we have to go through and tell it how many conductors we expect to have in our first harness that we're looking at. At any point, if you put in the wrong number or need to change it, you can do so. There's a button that allows you to do that. But for this analysis, I'm going to use 24 cables. So this is our overall harness. The harness has several branches, as you can see, but the individual cables only route from one box to another box. So they only use certain segments of that overall harness branching. So what we need to do is tell it where the connections are for this first cable. And according to my spreadsheet, it says that it connects from an avionics box to the wingtip light. So I've selected the cables that route from my avionics box to my light, and you can see it highlights those lines showing where the routing is of that particular cable. Now I get to define what type of cable it is. So this is a gauge that you can select anywhere from 26 down to double aught gauge, and of course you can put in any other information that you might have on it. And then also you need to select the type of cable. Is it a coax cable, a TSP? In this case, we're assuming it's a quadrex cable, so it's a shield with 4 inner pins. And as I mentioned before, we have stored data for this type of cable, including shield radius, resistance, transfer inductance, as well as the internal conductor wire radius and resistances. Now, of course, you can use this information that we have, which we feel is a good representation of typical aerospace cables, or you can input your own. After you have defined the type of cable, you need to specify the loads or termination impedances associated with your interconductors. For this analysis, we're assuming it's all short circuit, so it's all resistive with a very low resistance is how we implement that. And we have 3 of these cable types, these 26-gauge quadrax that go from the avionics box to the light, or 2 of them, I'm sorry. So I'm going to make a copy of that cable, is what we did in that process. Now we're on to the next type, which is a 20-gauge unshielded wire. So I will specify the routing for this particular cable, select the lines that are used in its routing, pick the termination points of this particular shield or cable, and then I'll use a typical 2.5 milliohm resistance for that termination. And then I will also here adjust the cable type and cable gauge. So there is no shield information for this unshielded wire, which are oftentimes routed with twisted shielded pairs or other things. And we'll say OK for that bundle, for that particular cable. And we have 4 total of these, so I will make 3 additional copies that have the same routing and termination characteristics. And now we'll look at the next cable and specify its termination and routing position. So it's it does take some time to put this information in, but generally nothing is easy about cables. What this allows you to do is to simplify the imported CAD and then also very clearly select the termination and routing locations of your cable and give it specific properties associated with typical aerospace cables. And that's what this wizard is designed to do. So I'm going to fast forward a little bit because what we'd just be doing is repeating this selection of routing and specification of cable type parameter information. So I'm going to skip ahead a little bit and find where we've defined most of our cables. So we're on 20 of 24. So this is 23 of 24. You can see across the top of the screen of the M-harness GUI. And we'll select our final termination points. That's 22 TST, twisted shielded triplet in this case. Again, we're using shorted connections for those interconductors. And we have one more copy that we're going to define. And then after you've defined all of your cable routing and features, you can look at the packing of the individual segments. So if this is for segment 1, you can look at how you want to configure the conductors within your packing arrangement. And this cable pack tool allows you to modify the arrangement if you see fit. So you can move the conductors around and position them in any arrangement that you feel is necessary. It's hard to know exactly what arrangement to put them in because the packing is not controlled typically in installations of vehicles. So oftentimes it's quite random, and if you're trying to do an analysis, what we typically do is make sure that we have a particular cable type along the exterior of that harness bundle to sort of look at what the most severe coupling might be for that particular cable type. This tool also provides you the ability to define probes. If you want to look at voltages or currents on any conductor or segment, I'm just going to define one shield, one current, and then that's essentially it. So now we've created our input file and we've completed our definition of routing and cable properties for this harness that we're looking at. So now that we've defined our harness properties, we'll assume that we've also defined all our material parameters for the rest of our vehicle, and we're ready for simulation. For this one that I'm going to show, we did a nose strike for this aircraft and a left elevator detach in the empennage region. And what I want to point out is that with our analysis technique is that we can solve these problems faster than ever before. Everybody knows that the processors and computer memory are increasing as they do. We also have the ability to do parallelized computing. This can be done on cluster computers, but also on desktops. This simulation was performed on my desktop computer, which has 16 cores, and it was done in a parallel fashion and completed in about 8 hours, which is incredible for this size of problem to be able to be analyzed on a desktop computer. It just hasn't been able to be done in that fashion before. Its 50-millimeter mesh size was used, and it had 280 million cells, and it's about a 7-gigabyte problem. So you have to have a very nice desktop to do that, but it can be done on desktops. One other feature that I'll point out is that we have a scaling technique in our software, which is called the gradual permittivity scaling, and that's applicable in low-frequency analysis problems, which lightning can be at later times, whereby you increase the permittivity of your problem space gradually and can adjust the time step of your problem in a similar fashion in order to achieve greater time steps at later time. And it works very well for lightning applications. So this huge aircraft model looking at indirect effects of lightning, normally, I mean, it's hard to say normally. It really depends on the type of computer you've had and what you're analyzing, but it could take a long time to analyze this problem. Now it can be done overnight. If you set the simulation to go overnight, come in the morning, and you have results. It's quite amazing. So with this model, I set up probes to look at different ATLs that you might be interested in for cable coupling. And so I looked at bundle currents, short circuit pin currents, open circuit pin voltages. And so for an entire aircraft model, including the details of the cable harnesses, we can look at a short circuit pin transient in one simulation. And I probed many more cables in this analysis, but I'm not going to go through all the results here for the sake of time. But you can gather transient data for your entire aircraft in a single simulation. And then if you're clever about the way you process that data, you can make nice spreadsheets or tables that can quickly allow the analyst to see where the worst case transients occur. And if you perform a matrix of simulations considering different attachment and detachment locations, you can quite efficiently analyze for what configuration, what attachment detach case you have, which transients will be the most severe. And this is a very convenient way to set your DO-160 test levels that you might have to do for system verification purposes. Along with any waveform that can be produced for cable transient structural currents, we have a lot of visualization tools that show you for your configuration current densities, cross-sections of electric or magnetic fields. Anything that you might want to look at visually can be produced. This includes animations that I showed a bit earlier in the presentation. So for this case, you can see that we did, in fact, strike the nose and take it off of the left elevator tip. So now that you have your results, the question always comes up is how accurate are those results? As I've showed in some examples, if you oversimplify your problem, you can give misleading or wrong answers. So everybody always asks, well, how accurate do I need to be? And that really depends on your program. If you're just looking for estimates of answers, or if you're using it for a certification type, you will have to go through a more detailed validation effort to determine how accurate your simulation technique is to an experimental configuration. And so we have done this on many aerospace platforms, and we have, over the years, seen an excellent agreement between our finite difference time domain simulation software and our analysis technique with the experimental side of things. And what this does when you do a correlation between your simulation and experiment is it allows you to set your simulation margins. This is where you can apply an uncertainty to your simulation and give a high confidence that your results are within this particular margin. There are techniques and formulas available to do a detailed quantification of your correlation. There's the FSV, Feature Selective Validation Technique, where you can look at amplitudes and action integrals to come up with a quantitative error value. This is not well defined. There are some suggestions in papers or publications that are available, but it's not defined in any standard. The IEEE standard for CEM validation does not cover lightning transients very well. It is being updated currently, that the task group is looking at that on ways to incorporate indirect effects of lightning for this validation. But what we have done historically and recently is to look at peak value comparison of experimental data and simulation data to get a sort of a overall correlation in that manner, and then look at a visual inspection of waveforms to see if they are similar. And this type of validation has been published recently for various aircraft certification programs, and what we have found is just what we consider an extraordinary correlation between experiment and simulation. That you can see the tab in the lower right, that 95% of our simulation peak values were within 6 dB of the experimental results. So we often speak in terms of dB. So for 6 dB, when looking at currents and voltages, that would be a factor of 2. And we have dug a little deeper and found that more than 80% of our correlation results were within 3 dB. So this is, you can see in that chart in the upper right-hand corner, with the red line being where experiment and simulation are equivalent, that through a large range of amplitudes from 10 amps up through 10 kiloamps, there is a very good or very sort of tight correlation between our simulation results and our experimental results. And we have found this level of correlation to be applicable on multiple vehicles in multiple environments. And we have a high confidence that we can reproduce this on different programs and vehicles. So this is the type of validation effort you might need to go through, where you set up a experimental object and simulate the same thing and then go through a data analysis to achieve your simulation margins. So I'll leave you with one final example. So in that validation effort we're referring to, we looked at an entire vehicle correlation where we simulated indirect effects of lightning, and they actually performed indirect effects of lightning tests on that. And so initially we had modeled some of the cables using a bulk representation where we captured the approximate diameter and approximate resistance of those cables. We found a larger than acceptable discrepancy in our results, being around 9 dB. And at that time we decided to go back and incorporate the more detailed information of the harness. So going from a bulk representation to a detailed harness model. And we saw, just by changing that representation of the cable, we saw a very improved correlation between the simulation and experimental results, down within 3 dB, further justifying the need to represent the complexities of your cable harnesses, both the interconductor details and the appropriate branching associated with the harness in order to achieve accurate results. So what I've reviewed in this webinar are some different analysis techniques. I talked briefly about engineering estimates and how you can create canonical or submodels, but the main focus was on these high-fidelity full vehicle models. And they are easier than ever to import and develop and include the full complexity of cable harnesses in for your analysis. And we have in our validation heritage high confidence in the ability of these full vehicle simulations to produce accurate transient levels in your particular vehicle. And as I've tried to show through those demonstrations, that we have tools available that more rapidly allow the simplification of cables from original import and also definition of parameters for those harnesses using our M-Harness Wizard. So that's what I have for you guys today. I really appreciate everybody tuning in. We now will answer some questions that anybody would have, and please feel free to contact me directly on my email, cody@ema3d.com, or on my phone direct line, 720-974-1208. If you have any questions or comments or suggestions about what you've seen or heard today. Thank you all very much.